So we were I'll now get a cell, and that cell is a pancreatic cell of the pancreas. What do? I have there, that is the cell. Let me do this. These are pancreatic cells here. Next, I'm going to do two preparations. This is the first preparation. Here, I'm going to extract DNA. Okay. In doing this, I have to somehow open up the cell, open up the nucleus, and then extract the DNA. That's what I'm going to do. And let's say this is the DNA that I'm having here. This is the DNA that I'm having. And in that DNA, there is a certain portion which is the insulin gene. It carries that insulin gene. So here I have the insulin gene. I'll call it gene of interest, because that is the gene I'm interested in. Are we clear? So that's the gene I'm interested in. What do I do next? Next, I'm going to I'm going to cut out the gene using restriction enzymes. We abbreviate them as RE. I'm going to cut out the gene using restriction enzymes, RE. Therefore, my gene will be just there like that. It is there now, isolated. That is my insulin gene. It is there. Okay? This is the first preparation. I go here now with my second preparation. My second preparation will involve something new here. My second preparation has something. Here we have a bacterial cell. That's a bacterial cell. And inside this bacterial cell, I have what I call a plasmid. Plasmid has circular DNA. That's what plasmids are. They are circular DNAs that are found inside bacterial cells. Are you following?
Yes, sir.
That's a plasmid inside there. It's a circular DNA. It means the bacterial cell you are seeing here, it has two things, two separate DNAs that are in it. This is one. So you have this one here. This is the first one. That's the first one. And here you have the second one. So the first one there is the normal DNA for this bacterial cell. The second one there is a plasmid DNA. This DNA is like a visitor. It comes in, that plasmid. It can enter the bacterium, it can go back out the way it wants. Sometimes it stays there forever. Sometimes when it's tired, it packs its clothes, it goes away. It goes and stay outside on its own. Or it might even go and enter another bacterial cell. So it's an independent guy. The plasmid can move anyhow. But the situation you are seeing here is as though you have somebody. This person has one head, okay? And that person has his normal brain, and he has a visiting brain somewhere. That visiting brain behaves like a plasmid. The normal brain is forever there. That is just like the DNA for the bacterial cell that you see there. So that visiting brain, what can it do? It can go outside. That's when the person has decided to become a fool, okay? It goes out. And sometimes it can come back in. That's how the plasmid behaves.
Okay.
So, because we know that this plasmid can do like this, and in the meantime, this plasmid is DNA, but it is circular DNA. What can we do? Mr. Plasmid there can move outside. Very good. So, can we force out that plasmid? First, we will force out the plasmid. We'll say here, we extract. We extract the plasmid. Okay? We extract it. And what do we have here now? We now have the plasmid. It is there. It is circular DNA. It's like that. It is DNA, but it's circular. And do you see that nevertheless, it has two strands. This is double-stranded. One strand inside, one strand outside. Okay? And now, next, I'm going to also do the same here. I'm going to cut. I'm going to cut open the plasmid with what? I'm going to cut open the plasmid using what?
Restriction enzyme.
Thank you. Using restriction enzyme. Okay. And that will be the plasmid. I've got it open. I've got the plasmid. It is open there. That's the plasmid. It's open. Now I'm going to, you see, I have the insulin gene there already. It is waiting. Do you see that?
Yes.
So I have the insulin gene. It's been waiting there. The plasmid has been delivered. I'm going to say now, I put probably in a test tube, insulin gene plus plasmid. I put them together. What am I going to have? I'm going to have here a plasmid there. And what am I going to have there also on top? The insulin gene. Do you see that?
Yes.
Now, this plasmid that you see here, is it still the same as the original plasmid that was there?
No.
No. Does it carry genes from the plasmid and from the insulin? Yes,
Yes.
it does. Therefore, have we combined, because this insulin gene is a section of DNA, it is DNA. Are we clear?
Yes.
And the plasmid itself is DNA. Okay? So, have we combined two unrelated DNAs? Yes, we have done so. Using what? Recombinant DNA technology to produce a plasmid that we shall now call a recombinant plasmid. Are you following?
Yes.
Good. Please don't worry. It sounds complicated because I need to explain things here and there. At the end, we shall put things into more perspective. You'll see that it's ABC, this thing. Very simple. Now, who is my plasmid? I call a plasmid here. The plasmid is what? Is a vector. A plasmid is a vector. And what is a vector? A vector is an organism that transmits a pathogen from one organism to another without being affected by that pathogen. Are we clear?
Yes.
So, the vector simply acts as a transporting vehicle. The word vector comes from vehicle. Just like the malaria parasite. The vector for the malaria parasite is what?
The mosquito.
Thank you. Precisely, the female, it is not me who's saying it, that was by God's grace. The female, you know, women are always problematic. The female Anopheles mosquito, okay?
Yes.
Yes, that is the one that transports the malaria parasite from an infected individual to a healthy individual.
Hello, sir.
Yes,
Um.
yes.
No, I thought it was passing.
Say again.
I thought my connection was
Oh,
like,
oh, okay. So, the plasmid here is like a vehicle transporting. What is it transporting?
the The insulin gene.
Thank you. The insulin gene is the passenger. Okay? So that's what the vector is. In your genetic engineering, you guys, they should have taught you all the terminologies here. But in the meantime, I'm sorting out all those terminologies that you were supposed to have been taught. Okay? One of which is the vector here. The vector, the plasmid vector. So that's who the plasmid is. Now, that's plasmid guy. We heard one story about this guy before. We said this guy can go out of the bacterial cell. It can even come back in again. You remember?
Yes.
Yes. So now, can we make this guy come back inside the bacterial cell? The answer is yes. So we shall use different methods because we need to put back this plasmid inside this cell. Okay?
Mm-hmm.
You need to put it back inside that cell there. We shall use here different methods of putting it back there. Oh, so I even had the beautiful arrow here, and I was not using it. Can you imagine? Just because of my enemies.
The enemy being who?
The one who's listening to me.
Hey,
The one who is hearing this beautiful voice. Thank you. Amen.
Oh,
So now I'm going to put back that plasmid inside there. Okay. Let's put the guy. There is the plasmid. It's a recombinant plasmid with the insulin gene. And we can have the normal DNA for that bacterial cell there. How do I put it back? I can use any of these methods here. It's not necessary for you to know the method, the methods, but just the names. I can mention transfection. Here we are going to use a bacteriophage. These are viruses that infect bacteria. We are going to first put the recombinant plasmid in the bacterial head, in the virus's head, and then the virus is going to just infect the bacteria and inject that recombinant plasmid into the bacteria. We can use electroporation. In this case here, we subject the bacterial cell to an electric shock. The pores, like the cell membrane pores, the pores on the cell membrane will open up and the bacterial cells will just drop inside there. Or we can make use of a gene gun. Somehow we load the plasmids into what we call a gene gun, and then we shoot it directly like a gunshot on the bacterial cells. Then it enters the bacterial cell. Any way by which you can put it in there, the plasmid goes in there. And later on now, we shall allow these bacterial cells to grow. And how do bacterial cells grow? Bacterial cells simply grow through mitosis. Are we clear?
yes.
Hmm?
Yes.
The bacterial cell will grow through mitosis to form other bacterial cells. And what do you think we'll find in these bacterial cells? We shall also find those same plasmids, because this is mitosis, no? Remember with mitosis, we say what? We say,
identical.
thank you, produces things that are genetically identical. Okay, cells that are genetically identical with one another and with the original mother cell. It means that the two cells that we shall produce shall have the recombinant DNA or the recombinant plasmid inside of them. Here we are just trying to multiply the recombinant plasmid. We can't just make many from scratch. We put it and then we say, Mr. Bacteria, you know how to do mitosis. Just do it the way you know best. And as it's multiplying, it also multiplies whatever is inside, which includes the recombinant plasmid. Bacterial cells multiply themselves like that, undergo mitosis every 20 minutes. It means every 20 minutes, 1 becomes 2, 2 becomes 4, 4 becomes 8, and so on. If you multiply like that, before you know it, you have millions of copies of the bacterial cell, meaning you have millions of copies of the recombinant plasmid as well. Meaning what also? You have millions of copies of what? The insulin gene. Do you understand?
Yes.
And when these bacterial cells undergo their normal metabolic processes, the insulin gene is also going to be active. And when it's actively giving out information for producing what?
Sorry, can you please repeat?
When the bacterial cell undergoes its normal metabolic processes, like it's like yourself, when you are alive, you are undergoing your normal metabolic processes. As it's being alive, the insulin gene also is active at that moment, is expressing itself. As it's expressing itself, it's giving out information because genes only give out information, okay?
Yes.
So the information that will be given out by the insulin gene, that information will be used to make what?
The insulin.
Thank you. And now it's making the insulin. Where is it making it? Is it making it in somebody? No. It's making it outside the person. Are we following?
Yes.
Most probably, this could be even happening in a test tube. A test tube is made up of glass. And in French, glass means vide. Sorry, vide. Glass. So here will be in vitro production of insulin. Okay, production of insulin in glass. It's just like in vitro fertilization. Fertilization in a test tube is made up of glass. Fertilization in a test tube. Like what they do for women maybe who can't get pregnant naturally, but who are producing healthy ova. Okay? Maybe the fallopian tubes are blocked. Then they extract the ova. They extract the ova. They put the ova in test tubes. They call the husband to come. Maybe he can come with the whole family. They sing joyous celebrations until he ejaculates in the test tube. Okay?
Yes.
And inside there, fertilization goes on. It's in glass. That's why we call it in vitro fertilization. So now we have millions of bacterial cells which are actively producing insulin. We shall now collect the insulin. We shall purify it and have a pure form of the insulin and inject it into the diabetic patients. Okay?
Yes.
So that was the difficult part. Now let us make things simple. What have we done so far? To produce insulin, we need 2 preparations. Are we clear? This is preparation number 1. First preparation, we are making here. This is first preparation. And here is second preparation, this side here with the bacterial cell. So first preparation, I want to make insulin. I don't know how to make insulin. Can I hire somebody? Yes. Who is that person? The insulin gene. Where can I get the person from? From the pancreas, because that's where we know that insulin is produced from. Okay, are we fine up to there?
Yes.
So with the pancreas, I first get pancreatic cells. I get pancreatic cells. From those cells, I extract the DNA. The DNA comes with so many genes and it's long. But am I interested in all the genes? No. I only want the insulin gene. So how can I get it? I cut it out using what? Restriction enzymes. I'm done with the first part. I'm done. I now go to the second part. I get bacterial cells. I know that some of them have plasmids, which are circular DNA. What do? I extract the plasmid out there. I want to turn it into a vehicle. Therefore, I must open it. So how do I open it? I cut it using a restriction enzyme. And with both of them here, I've already done my second preparation. I got my gene, I got my open plasmid. I simply combine them together. I can use some form of a glue that we call a DNA ligase. I can use adapters and linkers to combine them properly so that they can stick, the ends can stick properly. These ones are not part of your syllabus. They're not necessary, okay? I'm just trying to make you understand that these ends here must stick to the ends. The ends of the gene must stick to the open ends of the plasmid properly. So in a nutshell, I put these two together. It forms a new plasmid. Why am I saying new? Because it carries genes from somewhere else. Therefore, I'll call it what? A recombinant plasmid. I've recombined two DNAs. Insulin gene is DNA. Plasmid is DNA. I've recombined them. Okay? And now, what am I going to do next? Say again. Okay. Now, what do I do next? I will reinsert that plasmid in a bacterial cell. I allow the bacterial cell to multiply by mitosis, makes many copies of itself, consequently of the plasmid, consequently of the insulin gene. And when the gene is active, the bacterial cell releases insulin in glass that I extract, I purify, and I can use. Is this difficult?
No, because I'm even looking at the I want you to remember.
So it's very clear, right?
Yeah.
Yeah. Do you see the first time that I went through it, it sounded a bit complicated. But just because I needed to explain each aspect first. But now when I go over it the second time, you only have two preparations here. It's ABC. Cut out gene, have it there. Cut open plasmid, have it there. Join them together, put in bacteria. Leave bacteria to grow, gene expressed, insulin produced. It's straightforward. Okay? It's just people complicate their lives for nothing. This is very straightforward. Good. So this we come to the... Are you happy now?
Very happy.
You say?
Very happy. I'm very happy, thank you.
Okay, that's very good. Thank you for attending. Bye.
Thanks. Bye.
You're welcome. Let me just stop this recording.